Here is a machine that makes pictures at random. 28 by 28, one gray value per pixel. Every image it could ever produce lives somewhere in this space. Every photograph ever taken, every page of every book, every face you have ever seen, and yet watch. Nothing. Not one digit. Not one recognizable thing. The good pictures are all in there. They are just impossibly, vanishingly rare. Finding one by luck is not a long shot. It is not a shot at all. To find them, stop thinking of an image as a list of numbers and start thinking of it as a single point. 784 dimensions, one axis for every pixel. Scatter points at random through that space and you get noise, everywhere, without exception. But the images that mean something are not scattered at all. They lie together on a thin, curved sheet, a vanishingly small region of the whole. Learning to generate pictures means learning the shape of that sheet. So here is the plan. Build a small space we control, call its points codes, and a function that turns any code into an image. Then we want two things from it. 1. Every real image should have a code somewhere in that space. 2. Every code in that space should give back a real image. The first wish turns out to be easy. The second is the one that breaks, and almost all of this film is about why. Start with the obvious machine. An encoder narrows the image down step by step, 784 numbers, to 256, to 64, and finally to just 2. Then a decoder widens it back out again. That narrow middle is the whole point of the design. Two numbers cannot possibly memorize a picture, so the network is forced to find structure instead, and there is only one instruction: make the output match the input. Train it, and watch what comes out. At the start, the output is just the average of the entire dataset, a gray smudge that hedges every bet at once. Then the loss falls, the smudge sharpens, and after a couple of thousand steps, a recognizable digit comes out the other side. This is a real training curve from a real network, not an illustration. Two numbers in the middle, and the shape survives the squeeze. Though as we will see, not every digit is so lucky. Now, the interesting part. Where did it actually put everything? Here are 3,000 test digits, plotted by their two codes, and colored by which digit they happen to be. The good news is real. The same digit lands in the same neighborhood, and nobody ever supplied the labels. It found that structure alone. But look now at what is not there. Between the clusters lie great empty regions the encoder simply never used. Those gaps matter enormously, because the decoder will happily accept any code you hand it. Pick a point inside a cluster, and you get a clean digit back. Fine. Now pick a point in the middle of one of those empty regions, and decode that instead. Nothing. A smear. The decoder was never once asked about this address during training, so it has no idea what belongs here. And worse, it does not know that it has no idea. The same failure again, now in slow motion. Take two digits, take their two codes, and walk in a straight line from one to the other, decoding every step along the way. The ends are sharp, because the ends are real data the network has seen. But the middle crosses that empty country, and it falls apart completely, a ghost that is neither one shape nor the other. This space is not continuous. It is a set of islands, with nothing in between them. And you can see exactly why, written in the loss function itself. Look carefully at what it mentions: an image from the training set, and that same image rebuilt. That is all it mentions. Every point that is not a training image contributes nothing, is never scored, and is never once asked about. We built a lookup table with a compression tax attached, and then acted surprised when it could not answer a question we never asked it. Here is the whole idea of this film in one single move. Stop sending each image to one single address. Send it to a region instead, a little cloud of plausible codes with a center and a width. Now the decoder is not being asked about one isolated point. It is being asked about a whole neighborhood at once, and neighborhoods, unlike points, can touch each other. Concretely, the encoder stops returning a code and starts returning a description of a cloud, a center, which we call mu, and a width, which we call sigma. The actual code is then a random draw from that cloud, and because the draw is random, the decoder must learn to cope with everywhere the cloud reaches, not merely its middle. Do that for every image in the dataset, and the clouds begin to overlap. Those overlaps are what stitch the whole space together. It helps to tell the story backwards, the way the model itself does. Step 1, draw a code at random from something simple, something with no structure in it at all, a standard bell curve, centered on 0. Step 2, push that code through the decoder to get an image. That is the entire generative model, start to finish. Every picture it will ever make is some code you never saw, run through one fixed function, which finally gives us a number to aim at. How likely is a real image under this model? You take the chance of drawing each possible code, multiply it by the chance that this particular code produces this particular image, and then add all of that up over every code there is. Make that number large for real images, and the model has genuinely learned your data. There is only one problem with it, and it is a serious one. You cannot compute it. Try the obvious thing. Chop the space into a grid and add up the pieces one by one. In one dimension, that is 10 boxes. In two dimensions, 100. In three, 1,000. The exponent is the number of dimensions, and real latent spaces have dozens of them. At 64 dimensions, you would need 10 to the 64 separate evaluations. The observable universe contains only about 10 to the 80 atoms. You are not computing this integral. Not today and not ever. Then, just sample it, you say. Take random codes and average them. Here's the problem with that. Fix one image and ask every possible code how well it explains that image. This is the actual surface, computed from the trained decoder. Almost all of it is dead flat, and essentially all of the value sits in one tiny spike. Throw darts uniformly and you will miss over and over again. In 64 dimensions, you would wait longer than the universe has existed. So do not search for the spike. Ask for it. Train a second network whose entire job is to look at an image and point straight at the region of codes that could explain it. That is the encoder, and it now has a proper job description. Approximate the true posterior. Classical statistics would run a fresh optimization for every single data point, one at a time. This shares one single set of weights across the whole dataset. It is called amortized inference. Now, two forces pull on this space in opposite directions. Reconstruction wants every image kept well separated and every cloud kept tight, because that is how you rebuild things accurately. But push far enough and the gaps come straight back. The prior wants everything packed near the origin and spread wide, because that is the shape we will sample from. But squeeze too hard and every image blurs into its neighbors. The VAE lives in the truce between them. The referee between them is a quantity called the Kullback-Leibler divergence, which measures how far one distribution sits from another. Yellow is where we want the codes to be. Red is where one particular image actually puts them. That mismatch carries a price, and the price is never negative. Slide the red curve across, and the price falls. Widen it to match, and the price falls all the way to 0. For two bell curves, this has a closed form. Here is what that pressure actually does measured on real trained models. On the left, the plain autoencoder free to sprawl into whatever shape happens to suit it. On the right, the same architecture, the same data, the same bottleneck, with only the KL term added. It has been pressed into a compact blob, centered neatly on the origin. That circle matters enormously, because it is exactly where our random codes will come from. On the left, a random draw mostly lands on nothing at all. On the right, it simply cannot. Now, The mathematics pays off. We could not compute the log likelihood directly, so instead we split it into two pieces, a term we can compute, and the distance between our encoder and the true posterior. That second piece is a distance, so it can never be negative. Drop it, and whatever remains can only be smaller than the thing we actually wanted. That is a lower bound, the evidence lower bound, and it works out to be exactly reconstruction minus KL, the two forces, written down. Think of it as a floor and a ceiling. The ceiling is the truth, sitting at a height we can never directly measure. The blue floor is our bound, which we can compute exactly, on every batch. The green gap between them is precisely how wrong our encoder currently is. Training pushes the floor upward, and the ceiling has no choice but to rise along with it. You never once see the ceiling. You only ever push the floor. One obstacle left, and it is a real one. Training needs gradients, and there is a random draw sitting in the middle of the network. You cannot differentiate through a coin flip. The gradient reaches the sampling step and stops. The fix is beautifully simple. Move the randomness out of the path. Draw the noise separately. Then compute the code as mu plus sigma times that noise. The randomness still arrives, but from the side. Now the gradient has a clean road home. This is the reparameterization trick. So here's what the machine actually minimizes for every image in every batch. One term asks a simple question: did the picture come back? The other asks a different one: did the code stay somewhere we can find it again? And sitting in front of that second term is beta, a dial that decides which of the two forces gets to win. Turn that dial, and you get a genuinely different model out the other side. Watch it actually happen. This is the real latent space during real training. At step 0, it is a shapeless blob, because the network knows nothing yet. Reconstruction pulls the classes apart so that it can tell them from one another. The KL term keeps folding them back toward the circle. By step 2200, they have settled into a shape that is both organized and reachable at the same time. Both forces got what they needed. Now the payoff. Take the trained decoder, walk across the latent plane in a regular grid, and decode every single point you pass along the way. This is the entire model, drawn out flat in one picture. Every square you see is a genuine decoder output. Nothing selected, nothing cleaned up, nothing rearranged. Move a little, and the shape changes a little. And crucially, there are no dead zones anywhere. You can put your finger down anywhere in this square, and something sensible comes out. Which brings us back to the test that started all of this. Draw codes from the prior, decode them, and simply look at what you get. On the left, the plain autoencoder, smoke. Its code sprawled somewhere else entirely, so our draws mostly land on nothing. On the right, the VAE, digits it has never seen before, assembled out of pure noise. Same architecture, same data, same bottleneck. And the walk between two digits, the one that fell apart an act ago. The top row is the plain autoencoder crossing its empty country. The middle of it is nobody's digit at all. The bottom row is the VAE, making exactly the same journey between exactly the same endpoints. Every single step along the way is still a digit. One shape becomes another without ever once leaving the data. That is what a continuous latent space actually buys you. Now turn the dial and watch. The same model, trained 3 separate times, with only beta changed between them. Low beta leans on reconstruction, crisp digits, but the space starts tearing open again. High beta leans on the prior, beautifully tidy, and almost nothing left to say. The numbers underneath are measured, not guessed. They are how much information each latent space actually carries: 12.5, 6, and 2. The middle one is the truce we were looking for. Push that dial too far though, and something very specific goes wrong. At beta equals 10, Every image's cloud has been squashed down on top of every other image's cloud. The codes now carry almost no information whatsoever, and when you sample, the decoder produces the same soft shape every single time. It has stopped listening to the code entirely and simply draws the average digit instead. This failure is common enough to have earned its own name, posterior collapse. Time for the honest complaint. VAE outputs are soft, and here is the reason. All of these are the same digit, and all of them are plausible. If the decoder is uncertain which one it should be drawing, the loss rewards it for hedging. And the hedge that minimizes squared error is the average of the options, which is blurry. Again is punished for hedging, so it commits and stays sharp. Blur is not a bug in the code. It is the objective being obeyed. But softness is not the only thing worth having, and here is a use that the blur does not spoil at all. A model trained only on digits will reconstruct digits easily and will struggle with everything else. Green is the reconstruction error on real digits. Yellow is those same digits with their pixels shuffled. Red is pure noise. The distributions barely touch each other. Draw a line and you have an anomaly detector, trained without a single example of the thing you are trying to catch. Second use. Filling in whatever is missing. Cover the bottom half of each image and hand the model only the top half. It encodes what it can actually see, and then decodes a whole complete image. Here are the completions it produced, and here is what was genuinely there underneath. It is not copying, it has no access to the answer at all. It returns what is most likely, given the rest. The same trick fills gaps in medical scans, sensor logs, and survey data. Third, describing things briefly. An image here is 784 separate numbers. The encoder says very nearly the same thing using only 2. And those 2 are not arbitrary coordinates either. Plot them, color them by digit, and you find the classes have separated all on their own. Nobody ever supplied the labels. The model worked that structure out from raw pixels alone, because organizing the space was the only way it could do its job. You can even read what the 2 coordinates mean. Hold the second one fixed and sweep the first. The shape slides smoothly from one form into another. Now hold the first and sweep the second. A completely different property changes instead. 2 dials, and between them the whole alphabet of digits. With more dimensions, these become the things you would actually name out loud. Slant, stroke weight, style, which is what people mean when they talk about a disentangled representation. Fourth, asking for something specific. So far, the model draws whatever it likes. You get a digit, but never the digit you actually wanted. Feed the label in alongside the code to both the encoder and the decoder, and now you can finally ask. The code is left to carry style, the slant, the thickness, the shape of the loop, while the label carries identity. That is the conditional VAE, and it is the very same machine with one extra input. And here is where this idea ended up mattering most. Modern image generators do not work in pixels. Pixels are far too expensive. An autoencoder squeezes the image down to a small latent first. All the expensive generative work, the diffusion process, happens in there on far fewer numbers. Then the decoder blows the result back up. That squeezing step is an autoencoder of exactly this family. The VAE is the quiet half of the picture-making machine. It is worth being clear about where this sits among its neighbors. A VAE gives you an encoder, trained stably, and produces somewhat softer images. A GAN has no encoder at all, is notoriously difficult to train, and produces very sharp ones. Diffusion trains stably and looks superb, but sampling from it is slow. Only one of the 3 gives you a way back in, a map from an image to a code. That encoder is why VAEs keep turning up inside other systems. So the whole argument, once more. We wanted to generate images, which meant we needed a space we could sample from. Squeezing images into a small space gave us codes, but isolated points, with holes lying between them. Sending each image to a cloud instead forced the decoder to handle whole neighborhoods. Pulling every cloud toward one simple shape made the space compact and reachable. And now every point in that shape decodes to something real. Each step was forced by the one before it. If you keep one single sentence from all of this, keep this one. An autoencoder learns where the data is. A variational autoencoder learns where the data isn't. That is what the KL term is really doing, underneath the mathematics. It is a statement about the empty space, an instruction that the gaps must be filled, and that the whole region has to mean something. That is the entire difference, and it is the entire point. Everything you have seen here was rendered from a model trained from scratch for this film. A small variational autoencoder, written in plain NumPy, trained on handwritten digits. The latent maps, the samples, the interpolations, the failures and the collapses, every one of them is a measurement, not an illustration. And the strange part is that all of it followed from one small refusal. The refusal to give each image a single address,